Press record. Yeah. Okay. So we're going to go over the definition of a function, how to evaluate a function, what else? How to read the graph of a function, and how to find the domain of a function. So we're going to cover all of that today. Okay. So definitions of a function. First, we start off with the definition of a relation. A relation is a set of ordered pairs. So an ordered pair would be something in terms of X, Y. That would be an ordered pair. And the domain is a set of all first components of a relation. So in this ordered pair, domain corresponds with the first part of your ordered pair, X. So domain will always belong to X. And then range is the second component of your relation. So range would always relate to Y. So whenever you're finding the domain of a function, you're finding the X values. And whenever you find the range of a function, you're finding the Y values. And I can do that. Boom, and boom. There we go. So domain goes to X and range goes to Y. Okay. And now the definition of a function. A function is a relation in which each element of the domain corresponds to one and only one element of the range. To put it simply, the first components of are all unique. So your X values are all unique. So in order to be a function, an X value must have only one Y value. Okay. So I'll say it again. To be a function, an X value must have only one Y value. So look at our blobs below. These are the pictures of what a function is or represents. So agree with that. So the first picture represents a function. So here in the first glob is our X values, and in the other glob is our Y values. So this is a function because I have an X value that goes to one Y value. I have another X value that goes to one Y value. And then again, I have another X value that goes to one Y value. And it's okay if multiple X values share one Y value. Remember, to be a function, one X has only one Y. And then another X value goes to 4. So what we're saying is that all of these X values have exactly one Y value. That is the definition of a function. And yes, multiple X values can share the same Y value as long as it's a single Y value. Okay. And now what doesn't represent a function is the next picture. This is not a function. And let's see why. We have an X value that goes to one Y value. Perfect. We have another X value that goes to one Y value. Good. We're looking good so far. But then we have an X value that goes to how many Y values?
Two.
So we have one X value that goes to two Y values, which means this is not the definition of a function. So this is why this picture represents not a function and this picture represents a function. So again, just to keep it really simple, to be a function, one X value must have one Y value. That's it. Okay. Any questions on that?
No, sir.
Okay. So next, here we are given the graph of a function. And it's very important to know how to read a graph and know what it's asking. So For A, this says find f of 0. So this is our function notation. And this function notation belongs to this graph on the right. So when we are ever given function notation, it's in the form of f of x. So what we're saying is that when you're given an x value, we want to know what the output is. So when you have an x value, the output should always be a y value. So that means when we say find f of 0, this means we are going to look where x is 0 and output the y value at that x value. So if you look at where x is 0 on the graph, which is right here, what is the y value that is associated with that?
0.
0. That's it. When x is 0, y is 0. Okay. Let's try it again. B, find f of 6. This means you look on the graph and you find where is 6 at. So here is where x is 6. And again, we find where x is 6 and we want the y value. What y value is associated with that?
0.
0. Okay. There we go. Now, C, is f of 3 positive or negative? So what we're saying in this question is when x is 3, is your y value above the x-axis or below the x-axis? And now technically, we don't see a 3 on here, but we can place it. So if I just drew a little 3 in here, and then associated this y value down here, which I'm just going to call f of 3. All we want to know is that value positive or negative? So is our point f of 3 above or below the x-axis?
Below.
Below, which means it would be
Negative.
negative. That's it. Okay. And now, D, for what values of x is f of x equals 0? So now this is asking the question backwards. This is saying that when y is 0, what are the values of x? So when y is 0, what are your values of x? So look at the graph and find where y is equal to 0. We have y 0 there, we have y at 0 there, and we have y at 0 there. So what are the x values associated when y is 0?
0, 4, and 6.
There you go. 0, 4, and 6. Okay, perfect. And now E says, what is the domain of f? So remember that from the above definition, domain corresponds with your x values. And whenever you state domain and whenever you state range, you always start with the smallest possible value. And when we are reading a graph, we read graphs from left to right. So when I'm looking at the domain, I'm looking at my x values. So if you look at this graph, what is the smallest possible x value that we have?
Negative 4.
Negative 4. And we end at the largest possible x value, which is
6.
6. There you go. That's our domain. It starts at negative 4 and it ends at 6. You only state x values. Okay. Oops. All right. Now we want to know what is the range. And range deals with y values. And just like domain, we look for the smallest value. So here we're looking for the smallest y value. What is that going to be?
-2.
-2. And then what is the largest y value?
5.
That would be x. But what's associated with that?
3.
Oh, 3.
3. There you go. So we'd start at -2 and we would end at 3. We don't go anywhere past 3. Okay. So that's domain and range. Remember, domain is x values, range is y values. Okay. And then we say, what are the x-intercepts? Okay, what are the x-intercepts? Well, x-intercepts lie on the x-axis. You can only have an x-intercept when y is equal to 0, or f of x is equal to 0. So x-intercepts, again, lie on the x-axis. And if you're on the x-axis, y or f of x is always 0. So what are my x-intercepts from this given function?
0, 4, and 6.
Good. 0, 0, 4, 0, and 6, 0. And I think we'll have to state them as points. Okay. That's an x-intercept. X-intercepts lie on the x-axis. Now H, what are my y-intercepts? Well, if x-intercepts lie on the x-axis, then y-intercepts must lie on the y-axis. And you can only have a y-intercept if x is equal to 0. And if you look at your y-axis, what's the only point you see?
0, 0.
That's it. 0, 0. Okay.
So there's nothing like that's the reverse of a function where
We
it's
have an
the y-
inverse function. We can have an inverse function.
And is that where you're finding the y-intercepts?
No. So inverse is something totally different. I don't even know if we'll do those in this class. But yeah. So, but other than that, all we're doing is finding x-intercepts, y-intercepts. And if you see by our graph, you can only have one y-intercept, but you can have multiple x-intercepts. Okay.
Or also it wouldn't be a function if you had multiple y-intercepts.
Exactly. Exactly. Good. All right. For what values of x does f of x equal 3? So remember, this asked the question backwards. This wants to know when y is 3, what are the values of x? So look on the graph where y is 3, and what is the value of x associated with it?
5.
Good. There you go. Nowhere else, right? And then the next one, the same. For what values of x does y equal -2? So again, when y is -2, what is our value of x?
2.
2. There it is. And that's it. This is how you read a function. This is how you read a graph and answer the questions in function notation. Okay. Any questions on this page?
No, sir.
Okay. All right. So now we're going to talk a little more about the domain of a function. And when you find the domain of a function, you're finding where does the function exist? On what x values does a function exist? So the domain of a function is the set of all the first components or x values for which when evaluated will result in a value in the range of the function. For most polynomial, rational, and radical functions, we look for all values of x that will result in a real number answer. We work to exclude a result of 0 in any denominator and force positive values under radicals with even powers or indices. So I'll show you what all of that means if that sounded foreign. So it's basically telling us what functions we're going to be given and how we're going to find the domain. That's all that paragraph is saying. Okay, so for example 2, it says find the domain of, and not all of these are rational. So we're just going to mark that word out here. We're just going to say find the domain of each function. And write your answers in interval notation. Okay, so let's go ahead and get started with A. So in order to find the domain of a function, you have to know what function you are working with, what type of function you are working with. So for the first one, f of x equals 4x cubed plus 5x minus 7. Does anybody know what type of function this is?
Trinomial?
It is a trinomial, which is good, but a trinomial still falls under another category. And a trinomial, a binomial, a monomial, whatever type of nomial we have, they all fall under one category.
Polynomial.
Polynomial. Okay. Now, in order to be a polynomial function, all of your exponents must be whole positive numbers. That is the definition of a polynomial. Your degrees, your exponents, your powers, they must be whole numbers and they must be positive, which we see that 3 and 1 are definitely positive numbers and they are whole numbers. Okay, that's just a brief definition of what a polynomial is. So first, I'm gonna write what function we have. We have a polynomial function, and the domain of a polynomial function, this one's easy. The domain of any polynomial function is the set of all real numbers, or the interval notation of -infinity to infinity. And this will be the domain for any polynomial function. We can say all real numbers. Okay. And what you're seeing here is called interval notation. Okay. And we've seen it before. We saw it in 1.1 or 1.2 when we were doing the inequalities. We saw how to put our answers into interval notation. So this is how we're going to write our domain. Okay. So once again, for any polynomial, your domain is always going to be from -infinity to +infinity, all real numbers, because these functions go on infinitely. Okay. B, now we have some work to do. And we are given f of x equals 2x over x minus 3. Now this function has a special name. It has a polynomial over a polynomial. And the fanciest word we can say for fraction is the word rational. So if you're ever given a fraction as a function, then the appropriate term is rational. This is a rational function. It's just a fancy word for fraction. Okay. And now, if you think about fractions, what number can never ever be in the denominator of a fraction?
0.
0. Good. So if you're ever given a rational function, you will take the denominator and set it equal to the number that can never, ever be down there, which is 0. And all you have to do now is solve for x. So our domain is going to be x equals 3. Okay, but there's more to it, because what would happen if we actually plug 3 into this function? If I said f of 3, I would get 2 times 3 over 3 minus 3. This would give me 6 over what number?
0.
0. And can we have 0 in our denominator?
No, sir.
No. So guess what our domain is going to be? X cannot equal 3 because it makes the denominator 0. So what this domain is telling us is that we can be any number we want except for which one?
3.
3. Good. But now we have to put this into interval notation. And to help you put it into interval notation, I'm just going to draw a number line. We've seen number lines before. So my number line is going to start at negative infinity and end at infinity. And right in the middle, I'm just going to put 3 with the open circle because we cannot be equal to 3. So whenever you write, go ahead.
Does that mean that when it's 3, there's multiple y, so it's not a function?
Oh no, it's a function. Just what we're saying is that when x is 3, the whole function is undefined. Because remember, any number over 0 is always undefined. So it exists everywhere else except that 3, when x is 3. Okay. Okay. So now, to put this into interval notation, we're going to look at the number line I drew above. And we can be, and when I say we can be any number we want, we start at the smallest possible number on the number line. And that number is going to be negative infinity. And now, as I come up the number line, I have to stop at what number?
3.
3. And then I'm going to continue after 3 and head towards infinity. So now, what we're going to have to do is use a special notation. We're going to say our domain is negative infinity to 3 union 3 to infinity. So that little symbol there means union. It's telling us the sets of numbers, the sets of x values that rational function exists on. And that is how you find the domain of a rational function. All right. And hey, why not? Maybe more visual. I have Desmos up. Why not? Let me go ahead and graph that function just to show you where it exists and where it doesn't. Watch this. All right, we're going to clear all of that out. And I'm going to do 2x over x minus 3. And look what happens. As we get close to 3, can it show it all on here? Probably not. Actually, I'll do this here. I'll say x equals 3. Okay. So that blue line is 3. And look what happens. As we get closer and closer to 3, we will never, ever touch it from the left side and from the right side. So this is showing us graphically that this function does not exist at 3. It will never, ever touch 3. So there is a visual representation for you. Okay. All right, let's move on. C, f of x equals the square root of 3x minus 8. Okay, so the square root is an even root. So the type of function we are dealing with is going to be called an even radical. An even radical. So to find the domain of an even radical, well, let's see what we know about the square root. Can you take, actually, I'll write this to the right. If I just had the plain old square root of x, can you take the square root of a negative number?
No.
No, which means that if you cannot take the square root of a negative number, this means you have to stay above what number?
0.
0. Good. So the square root will work for numbers above 0. But then, can you take the square root of 0?
No.
Think about it.
Or
What do you
yes,
think the square root of 0 is?
0.
0.
Good. So for the domain of any even root function, including the square root, you will take whatever's inside the house and set it greater than or equal to 0. Greater than, to avoid negative numbers. Equal to, because we can take the square root of 0. So let's go ahead and do that. And we're going to set 3x minus 8 greater than or equal to 0. And all we have to do now is solve for x. 3x is greater than or equal to 8. Divide by 3. And x is greater than or equal to 8/3. Okay. There's our domain. But now we have to put it into interval notation. So once again, I'll just draw a number line. Here's negative infinity. Here's infinity. And remember that greater than or equal to will get a bracket. Here's 8/3. And if I have to be greater than 8/3, am I heading towards infinity or am I heading towards negative infinity?
Infinity.
Infinity. So this means that for my interval notation, we will start at bracket 8/3 and head towards infinity. There it is.
So the domain is x greater than or equal to 8/3, correct?
Correct. So both of
Okay.
these represent the domain. These two represent the domain. One is called interval. The other is called set notation. So this is called set notation.
Okay, thank you.
We can say something?
I said thank you.
Oh, you said thank you. I thought I heard somebody else too.
Yeah, I was gonna ask, so on Math Lab, are we gonna typically be getting asked for the set notation, then to do the line and then the interval?
I think it's just gonna want interval notation,
Okay.
but I guess I should forewarn you in case it does ask for interval notation. I mean, if it does ask for set notation, well, there is a fancy set notation and it's gonna have it set up for you already. So it's gonna have fancy brace for all x such that, and all you have to input is the inequality, x greater than or equal to 8/3. So my math lab will have this part and this part set up, I think all you have to do is input the inequality there.
So would
So-
you ever see a set without those squiggly brackets?
I mean, I call what I circled here, I called shorthand set notation, which
Okay.
is fine. But on my math lab, if they ask you for set, it's going to be set up like that.
Cool.
But it's not too crazy because all you really have to do is just input that in straight into there. Okay. Okay. Excellent. All right. Next. D, 3x squared over x squared plus x minus 6. What type of function is this again?
Polynomial.
It's a polynomial over a polynomial. What is the good? I was like, what is the fancy word for fraction? Rational. And we know that to find the domain of any rational function, you take whatever's in the denominator and set it equal to what number?
0.
0. Okay. And now our job is to solve for x. Well, hey, look what we're given. We are given a quadratic function / equation, which means we learned how to factor this last week. We can factor quadratic equations. And these are the easy ones to factor because all we have to know are the factors of the last term. What are my factors of 6?
1 and 6.
2 and 3. And now which of these factors can make positive 1?
2 and 3.
2 and 3. And look, plus minus means that when I set this up, you'll get x plus a number and you'll get x minus a number equal to 0. Well, in order to get 1, is the bigger number 3 going to have to be positive or negative?
Positive.
Positive. And 2, the smaller number, will be negative.
No.
There you go. Factored. X squared negative 2 plus 3 gives me 1, and we're good. It's completely factored. It's correctly factored. And now all we have to do is set these terms equal to 0 and solve for x. So x plus 3 equals 0, x minus 2 equal to 0. And what are my values for x?
-3 and +2.
-3 and +2. But since this is from a rational function, can we actually equal -3 and can we actually equal 2?
No.
Because they'll make the denominator what number?
0.
0. Good. So cancel that, cancel that. So what we're saying for this domain now is that we can be any number we want except for which 2?
-3 and
-3 and 2.
Good. -3 and 2. All right. Well, I guess I should set you up for this. Let's do set notation first. We say for all x such that x can't equal -3 and x can't equal 2. And then for interval notation, let me show you the number line. Here's -infinity. Here's +infinity. And on the number line, I'm going to put -3 and 2. And now, what is my interval notation going to be? What number am I going to start at?
-infinity to -3, and then unity
Union. And then start where?
2. 2
Careful,
infinity.
because we stop here And then
Oh.
we continue on there. So what's the next set?
So do you use
-3.
Negative
Yeah.
3 to union. And what's the last set?
2 to infinity?
There you go. There it is. So these are the sets of numbers where the function exists.
So is it typical for rational functions to give you specific numbers that you can't use, and then roots to give you greater than, equal to, and so forth?
Well, rationals, oh yeah, you're saying like with the typical functions, like rationals will give you numbers you can't use. And then roots, like radicals, will tell you whether you're going to be greater than or less than a number.
Okay, cool.
Yeah. Okay. Which brings us to the last one. Tricky, tricky. I'll leave that there for a couple of seconds, just in case you're still writing it down. All right, last domain problem. All right. Well, look at this. We have a mixture of functions. Once again, we have a fraction, which we can claim as rational, but what's in my denominator?
Negative.
Well, just the type of function. It's a rational with a
Root.
radical or root, whichever. I guess same thing, root, radical. Okay. So now, when we find the domain of this function, well, we look at the denominator and we have a square root and it's in the denominator. So all we have to do here is set it x minus 6. And normally we would set it greater than or equal to 0. But in this case, I can only set it greater than 0. Why is that? Think about a fraction. What number can never be in the denominator?
0.
0. So can I actually set this equal to 0?
No.
No.
No. So this one's a little tricky, right? So, and the only reason it's tricky is because it's in the denominator now. So we can only set it greater than 0, which means if you solve for x, x will be greater than 6. So for my set notation, well, that's easy. For all x such that x is greater than 6. For my interval notation, there's negative infinity, there's infinity, and greater thans or less thans get a parentheses. And if we have to be greater than 6, are we headed towards infinity or negative infinity?
Infinity?
Good, because we have to be greater than 6. So being greater than 6 takes you to infinity. Okay, which means for my interval notation, we have parentheses 6, comma, infinity, and done.
So we're never concerned with the numerator numbers. We never do anything with those.
For a rational function, no. Now, if you could reduce the function, then yes, but I don't think we do that in this class. So for now, for rational functions, you just worry about the denominator and nothing else. All right. I guess up here I could use set. Let me see. For all x such that X can equal 3. And then set notation for this one. I don't think it's going to have one for you, but if it does, it would say for all X such that X, oh yeah, they're just going to make you say all real numbers because this would be X belongs to the set of all real numbers. That's way too fancy for us.
And my handwriting's way too bad for that, honestly.
So that little symbol means that you belong to or you're an element of. And this double type R means the set of all real numbers. That's all it is. But I think if you get a polynomial, it's just going to have you say all real numbers or type negative infinity to infinity. Okay, that is domain. So again, one way to make it simple is know the function that you're working with. If you know the function you're given, then you'll be able to find the domain. Okay, you don't have to draw a number line all the time, but I did it as a visual to help you see what our domain would be in interval notation. So if it helps you, keep drawing the number line. If you get it just by looking at the notation, that's fine as well. Okay. Any questions before moving on from this page?
No, sir.
I'm sorry, I know you probably said this, but I didn't hear it. What does the little E mean before the all real numbers?
It just means element of or belongs to.
Okay, thank you.
Once again, I don't think my math lab will make you answer like that. If it does, well, now you've seen it, right? All right. Okay. So that's domain of a function. Now let's get into evaluating a function. So to evaluate a function means to substitute a number or a term in for X. More than likely, it's always X. So we say substitute or we say plug in, right? So let's go ahead and try evaluating this given function of x squared minus 4x plus 7. And let's evaluate it first by plugging in -3 for every x. So this says f of -3. This means you plug -3 in for every x and you simplify. So I'll write it here again. I'll say f of -3 is equal to, and whenever you plug in or whenever you substitute, you always put parentheses when you plug in. -3 squared minus 4 times -3 plus 7. Okay, we have substituted, and now from here we simplify. So here you get 9 plus 12 plus 7. -3 squared is +9. -4 times -3 is +12. And 9 plus 12 is 21. And 21 plus 7 gives me 28. Okay. So that is substituting a value in and simplifying. And what we're saying in function notation is that we're saying when x is 3, the value of y is 28. If we were to actually graph this function. So of course, there's always more meaning than just plugging numbers in. If I were to graph this exact point, it would be -3, 28. That's what you have just found. You found a point on this function. Okay. Okay, next, same thing. We are now going to take x plus 3 and plug it in for every x. Yes, probably sounds confusing. We take all of this and we plug it in for every x, just like the last one. So f of x plus 3 will give me x plus 3 squared minus 4 times x plus 3 plus 7. No different than the last one. We're just plugging in more terms now. And now all we have to do is simplify. Okay. So x plus 3 squared means we have 2. So x plus 3 squared has to be expanded. So x plus 3 squared means x plus 3 times x plus 3. And now we can distribute the negative 4. So this negative 4 is going to distribute to these terms. Negative 4x minus 12 plus 7. Okay. Now on x plus 3 minus 4x minus 12 plus 7, we're going to have to FOIL the x plus 3s. So we're going to FOIL those x plus 3s. So x times x is x squared plus 3x plus 3x plus 9. So we've just FOILed x plus 3 times x plus 3. And then we have negative 4x. And I'll just go ahead and combine these two already, which will give me negative 12 plus 7, which is negative 5. Okay. And now all we have to do is clean up one more time. And we'll start with our like terms. We start with x squared. There's no other x squareds on this line, so that comes down. And then we have 3x, 3x, negative 4x. That's 6x minus 4x, so we get positive 2x. And then the last numbers, 9 minus 5, we will get 4. And that's what we end up with. Nothing else we can do there. So what we're saying is that when you plug in x plus 3, the value of this function, or the value of y, is x squared plus 2x plus 4. And again, all we're doing here is we're just practicing how to evaluate and simplify a function. So any questions so far?
What makes this different from just saying x equals and evaluate?
Good question. Because here, since this is a function, we're simplifying. If it's x equals, we're solving.
Okay.
Right?
Yeah.
So there's a difference. There is a difference between solving and simplifying. And whenever you evaluate a function like we're doing right now, this is called solving. If I were to say, x squared plus 2x plus 4 equal to 0, then now we would be solving.
Okay.
Right? So there's a huge difference. That is a very good question. So there's the difference between simplifying and solving. Here, nothing has been set equal to 0, right? So that's one of your big giveaways on how do you know if you're simplifying or solving? Good question. Okay. And let's do it one more time. We are going to take x plus h, and again, plug it in for every x into that original function. Plus 7. Okay. And now it's been plugged in. Let's simplify. So x plus h squared means we have 2. So x plus h squared is going to be rewritten as x plus h times x plus h. And then distribute the negative 4. negative 4x minus 4h plus 7. Okay. And then once again, we have to FOIL the x plus h's. So x times x is x squared. X times h is xh. H times x is hx. And then h times h is h squared. Minus 4x minus 4h plus 7. Okay. And now all we have to do is combine like terms. And in here, there's not a lot. So here, there's no other x squareds. So that comes down. But then we have xh and hx. These are the same term, just written differently. So I'm just going to rewrite them as 2hx. And then here is h squared. So that's coming down. And then everything else is coming down. Minus 4x minus 4h plus 7. There you go. Nothing else combines, and it's as ugly as it is. Okay. And now, of course, this is going to lead into something bigger, which is right below. But to save you some time, if you ever see x plus h squared, and to save you about a good 10 seconds, know that x plus h squared will always FOIL out to x squared plus 2hx plus h squared. So this will save you some time whenever you see that, because we're about to see it a lot in the next two problems. But any questions on these three before moving on? Okay. Let's do it. Let's do it. Okay. So like I said, this leads into something bigger. So now we come across the difference quotient function, which is given by the formula f of x plus h minus f of x over h. So the difference quotient function is used in calculus. So you will see this again in business calculus. And all it means is that you are finding something called a derivative. But we don't have to worry about that in this class. For this class, all we have to do is practice the algebraic techniques of how to simplify the difference quotient. So it's heavily algebra based, which means that it was really good practice for students. And your main goal in the difference quotient, in simplifying the difference quotient, your main goal is to get rid of that h. That is your goal, to get rid of that h in the denominator. Okay. And the way we apply the difference quotient is in pieces. The first thing we want to find is what is f of x plus h. The next thing we want to find is what is f of x plus h minus f of x. Once we simplify that, then we take our final answer and we put it all over h. And if we did our work correctly, then we will be able to eliminate that little h down below. So that's your job. You got to get rid of that h. So let's go ahead and start it out. So we are given the function f of x equals 6x minus 2. Let's go ahead and apply the difference quotient to this function. And over here, I have the steps labeled already. we are going to start with f of x plus h. Hey, that looks familiar because that's what we just did above. We practiced plugging in f of x plus h. So here we go. F of x plus h, which means you're going to get, again, you're going to take that x plus h and plug it in for that x. So this is going to be 6 times x plus h minus 2. And now just go ahead and distribute that 6. We're going to get 6x plus 6h minus 2. And whenever you plug in x plus h, nothing will ever cancel on this step. So this is what we end up with on the first step. That's it. It's going to be ugly. This one's not that ugly right now, but it's always going to be ugly. Which means we can move on to the next step. We want to know what is f of x plus h minus f of x. Did we just find f of x plus h? It's what we ended up with in the last step. All of this is f of x plus h, which means we're going to start with what we found, 6x plus 6h minus 2. And now what we're going to do is subtract the original function. And whenever we plug something in, you must always put it in parentheses. If you forget those parentheses, you're going to mess the whole thing up. You're going to have terms that don't cancel, which is no good for you. So make sure you always put parentheses. Okay. Now, go ahead and distribute this negative. And you'll have negative 6 plus 2. Now, after we distribute that negative, you should have terms canceling. So look at this line and tell me what terms are going to cancel. Will those 6 x's cancel? Gone. Gone. Will these 2's cancel?
Yes.
Gone. Gone. What are we left with?
6H.
6h. And that's our answer for the second step, which means we are now able to go to the final step, which says find the difference quotient, which means we want to know what is f of x plus h minus f of x all over h. And f of x plus h minus f of x is what we left off with on the last step. So you're just going to put 6h over h, and guess what? What's going to happen to our h's? Gone. And all we are left with is 6. So what we're saying is that the difference quotient for this function 6x minus 2 is going to be 6. All right. Any questions on that process? And yes, it's a lot of algebra. So it's very, very easy to make a mistake. Okay. Go ahead and try out example 5. Let's see how far you get. Watch every step that you do. And I'll be right back.
Yes.
All right, I'm back. All right. Let's do this step by step. So you get 3 times x plus h squared minus 5 times x plus h plus 8. And if you're using that shortcut that we wrote above for x plus h squared, we know that that FOILs out to x squared plus 2hx plus h squared. Distribute that -5. And then just distribute that 3. 3x squared plus 6hx plus 3h squared minus 5x minus 5h plus 8. And that finishes the first one. Okay. And now for the second one, just rewrite it. So I'll have, do a different color, 3x squared plus 6hx plus 3h squared minus 5x minus 5h plus 8. And then we subtract the original function. Don't forget your parentheses. Okay. Then, to save some time, I'm just going to distribute the negative, and I'll just write this here. Negative 3x squared plus 5x minus 8. Okay. And then, once you distribute that negative, your terms will start to cancel. 3x squared, negative 3x squared, gone, gone. Negative 5x, 5x, gone, gone. 8, negative 8, gone, gone. Here's what we're left with from the second step. 6hx plus 3h squared minus 5h. There's a second one. And now we're ready for the final step. Find the difference quotient, f of x plus h minus f of x over h. And I have 6hx plus 3h squared minus 5 over 5h all over h. Okay. Now to properly cancel this, we're gonna have to factor out an h. We cannot cancel like this if you're thinking it. Oh, cross out, cross out, cross out. That would not be the proper way to cancel that h out. To properly cancel the h out, we're gonna factor it out, and you'll have h times 6x plus 3h minus 5 all over h. And here, your h's will cancel, giving us the final answer of 6x plus 3h minus 5. And that is the difference quotient, y'all. All the algebraic fun you could possibly have. Lots of letters, lots of numbers, lots of signs. Very easy to make a mistake.
Wait, so
watch.
why doesn't the h cancel out on the 3 in that one?
Because it was 3h squared.
Okay. Oh, I
Yeah.
get it. Yeah, I see that.
Good. No, good question. Good. So again, lots of algebra involved. Very easy to make a mistake. And one mistake could throw off your whole process. And you don't want to do that when they look this long. And the cool thing about the difference quotient, which you won't get until the next course, of course, is that the difference quotient finds the slope of the original function. So one of the best examples would be the first one. F of x equals 6x minus 2. That is in the form of y equals mx plus b. So if I just rewrote it as 6x minus 2, what is the slope of this function?
Six over one.
Just 6 over 1. And what did we find with the difference quotient?
6, which is
6.
same.
Crazy, right? So the difference quotient will find the slope of the original function. This one's just easier to look at because it's in this form already. This function, not so much. But all I'm showing you is that to make those connections, the difference quotient just finds the slope of the original function. But for now, for 1324, for you guys, it's just pure algebraic torture, which gets you set up for later on. So when you get to business cal, you're like, oh, I can do this with my eyes closed. No problem. Okay. Any questions on this page before moving on? All right. Let's get to our last page then. Woo! Whew, one big word problem. Okay. A manufacturer of a popular digital camera wholesales the camera to retail outlets throughout the United States. Using statistical methods, the financial department in the company produced the price demand data in the table below, where P is the wholesale price per camera at which X millions of cameras are sold. So here's this lovely XY chart where X is the number of cameras in the millions and P is the price that these cameras are sold at. Okay. So using special analytical techniques, an analyst obtained the following price demand function to model the table data. So that financial department modeled this data into a linear equation. P of X equals 94.8 minus 5X, where they're giving us a domain between 1 and 15 million cameras. So here they give us a domain. So now with this information, in A, it says, what is the company's revenue function for this camera and what is its domain? Okay, so revenue, in order to create a revenue function, I'll write it here. So to create a revenue function, the formula is always X times P. The amount of items X times the price P. So X is always the number of items. And P is always the price. Okay, so to create the revenue function, well, we already have all the information we need. We know we're selling X amount of cameras. And do we have an equation for P already? P is given as 94.8 minus 5X. There's our P value. Okay. Then to create this revenue function, all we're going to do now is just distribute this X and we're done. We get 94.8X minus 5X squared. This is our revenue function. Okay. And now it says, what is the domain of the revenue function? Well, if the domain of the price function is between 1 and 15 million cameras, then it only makes sense for the revenue function to have the same domain. The domain for the revenue function is also between 1 and 15 million cameras. Okay. Any questions on that one? So revenue is always X times P, the number of items times price P. All right, next. B, complete the table below, computing revenues to the nearest millions of dollars. So what we're gonna do now is compute the revenue function by plugging these values in for X. Okay. So good old trusty Desmos is going to work for this one. So let me go ahead and type in our revenue function. We have 94.8x minus 5x squared. And I'm going to use the table feature in Desmos, which means all you have to do is click that gear icon right above your equation and click the table button. And there we go. So now what I'm going to do here is just write in everything that we find. So we're typing in 1. Whoops. 1, 3, 6, 9, 12, and 15. All right, and I think we said just round. So as you see, they did it already for number 1. 1, we get 89.8, which was rounded to 90. 3, 239.4, which means we'll just say 239. 6, 388.8, 389. 9, 448.2, so just 448. 12, 417.6, so 418. And then 15 is just plain old 297. Okay, there you go. And those are the values for the revenue function given 1 through 15. Okay. Now, since we have created the table, it's going to ask us to graph it, plot the data in the table above, and then sketch a graph of the revenue function. Okay. So my X values are 1, 3, 6, 9, 12, 15. So I'm going to put that down below. This is going to be 1, and I think I can skip. Let me see. 1, 3, 6, 9, 12, 15. Perfect. And then my Y values start at 90, go up to 448, and then end at 297. So let's go by hundreds. Why not? The key word here is sketch. So I think I can skip on this too. 100, 200, 300, 400, and 500. Okay. Now let's go ahead and plot our revenue function. So first point is at 1 in 90. So that's going to be somewhere around there, 190. Next point is at 3 in 239. There's 250, so I'm put 239 somewhere around there. Then is 6 in 389. So I'm going to put that close to 400, somewhere around there. Next is 9 and 448. Let's put that on 450. Why not? 12 and 418, just a little above 400. And then 15 and 297. I'll just put it right on 300. Why not? And now here is my revenue function. There it is. R of X. Okay. And that is it, y'all. That is 2.1 functions. So if you got questions, stick around. If not, we are done.